So, we are trying to look into an example problem for HVAC. So, this is our control space, and we said that part of the air is recirculated and mixed with fresh air. And fresh air, how much fresh air we should be supplying? That is dependent by, governed by hygienic ventilation. There is a minimum amount of airflow, fresh airflow you require, thus governed by hygienics, hygienic ventilation requirement. So, if you look at this way, this is the exhaust and or exhaust or collection from the like already the air from the room, and part of it would be recirculated and rest all will be going out. So, here is the exhaust actually. So, this is the exhaust, this is recirculated fresh air. So, given in this fresh air, then you have a damper. Damper is essentially reduced down the velocity, right. So, damper. Then there is a filter. Filter would keep the particulate system out, that will not allow it to pass. And if the filter gets clogged, in fact, the fresh air, air combined mixed air supply tends to get reduced obviously. So, maintenance of this one is clean the filter from time to time. Then you have got if you need a heating, then there is a preheater in case of winter, but in summer this will not, we will be needing. Then there is a this is a cooling. So, cooling is through refrigeration, as I said. This the evaporator will be here, like which we discussed earlier, something like this. If I recollect, if we just want to recollect from, no, sorry, it is not here, but we said look at the cycle of refrigeration, and then cooling will be occurring. This will be cooling. So, cooling coil, the coil would be here where evaporation will take place, and it will cool this air here. And then you might cool it to a lower level in order to ensure some amount of condensation, because you want to control the amount of moisture content. Now, you want to reduce down the moisture content, then you have to go below the dew point, some moisture will condense, then you heat it back again. So, that is the after heater, and then this fan directs this. So, here the quantities are given. For example, in this one recirculated, it comes, room temperature is 21 degrees centigrade, and dry bulb temperature, and 14.8 degrees centigrade wet bulb temperature, right. And here this is fresh air, outside is 28 degrees centigrade dry bulb temperature, and 18.5 degrees centigrade wet bulb temperature. Now, this difference governs the moisture content, right, of the air itself. So, you mix them up, depending upon the proportion you mix, it might be somewhere in between temperature. So, 28 and 21, depending upon the proportion of the mix, the proportion of the fresh air and recirculated air. So, this is 28, this 21, it means that already 21 plus 28. So, proportion, obviously you can see if it is coming to 23, it is linearly varying. So, proportion of the recirculated air here is more, that is why it is close to the, if it was 50-50, 50% of fresh, 50% of recirculated, then it would be 21 plus 28 divided by 2, right. It would have been somewhere inside, linearly varying. Since more of the recirculated air we are using, essentially fresh air is only, because it will make it, cooling would be required would be more. So, therefore, fresh air we would supply whatever is minimum required to remove the carbon dioxide, etc., etc. So, here 21 and 23, you can see that ratio correspondingly, this is 2 difference and this difference is 5. So, 2:5, you can see the mass flow rate would be, and then after that what is happening, this is cooling, and cooling to a temperature of 14 degrees centigrade with wet bulb temperature as shown, how much it is, 11.5 degree, yeah, 5 degree. So, that is where it cools at, and then this fan, there will be some loss right, there will be some loss. So, its final rate would be sum total of this rate. Now, if you look at it, the rate is also given. How much is the rate? Because it is calculated and given. We will do a calculation separately. This is as 14.33 kg per second mixture, but before that the fresh air, the recirculated air was supplied at 9.51 kg per second, and fresh air is 4.82 kg per second. So, 20 is to, as I was saying, 2 is to nearly 2 is to 5, and total sum total will be the sum total of these two. 9 plus 4 is 30. Yeah. So, it adds up to 14 point. It's 14. It's actually, sorry, 9. Fresh air is 4.3 and this is 9.51. Sum total is making it 14.23. So, 14.23. And if you see the moisture, of course, wet bulb temperature does not give you moisture content directly. You have to go to the psychrometric chart or use equation. So, that is what normally the systems are. Let us look at an example problem. For example, you have a AC restaurant of this size is given as 1525 by 4 meter cube, and 300 persons in 3 sitting in 2 hours. Well, this only to find out how many people are sitting at a time, right. 3 sitting in 3 hours. Minimum desirable fresh air flow is 0.01 cubic meter per person, right, because that is what is required to remove, or that much fresh air you must supply to remove carbon dioxide or for all hygienic requirement. So, you can calculate the number of air changes anyway. The average U value of all the walls. Now, when we have walls, roof, etc., heat transfer takes place by conduction through these walls, and this is given in terms of, if you remember what we discussed in terms of fire also. So, it is K thermal conductivity into temperature gradient multiplied dt dx, let me call it, multiplied by the thickness L or K or whatever it is. Q is equals to K into A. K, Q is to K A dt dx, sorry, not L, there is no L, multiplied by area. So, that is the amount of heat will be, but then you have layered system. So, when you have layered system, did I discuss this sometime earlier in this class? Maybe not. If you have a layered system, then under steady condition we assume the flow is same, right, but temperature would be varying here T1, T2, T3, T4, etc., etc. And if parallel, if 2 walls are there, one wall, another wall, and they are subjected to same temperature difference, then heat flow will be sum total of the heat flow, like series and parallel model. So, under this condition you can define equivalent, we call it conductance of all the layers, and the formula is given as 1 by U is equals to L1 by K1, 1 by conductance I am saying so far, L1 plus K1 plus L2 plus K2, where L1, L2 etc. are the thickness of these ones, and K1 is the thermal conductivity. Now, this is, but then there is a fine air layer on both the sides, boundary air layer, and when you take care of their conductivity, equivalent conductivity, there will be convection and radiation which you can convert into equivalent conductivity. So, this is called surface conductivity. When you take that into account, so you write it like this 1 plus HO, where HO is the outside surface conductivity, equivalent surface conductance of the surface layer, plus surface conductance, not conductivity, or that is what you say. So, if you do that, and then you get what is called you get what is U value. So, 1 over U is given like this. In other words, I am not going to, because going into details of this is not part of this course. So, I am not doing this, but U A temperature difference gives you the amount of heat. UA, U is what we call U value or transmittance value, which is units is watt per meter square per degree centigrade, right, into area of the wall into delta T temperature difference, that will give me the amount of heat that will come in. So, if I want to find out the amount of heat cooling load, so essentially I would like to know. So, this is U value is average U value is given 1 by U is equals to 1 by Hi etc., sigma L by K, the formula is also given here, of exposed walls are 2 watt per meter degree Kelvin. The radiation heat gain through the glasses are given. If the radiation fall onto the glass, if I know intensity of radiation, because intensity of radiation is expressed in terms of watt per meter square. So, that multiplied by the area of the window or the glass will give you the amount of heat that will come in, multiplied by a factor, because glass will not transmit everything, only a fraction of it will come, we call it solar gain factor. So, that is why you have written A I theta. A is the area of the glass, I is the intensity of radiation, and theta is the solar gain factor, the fraction. So, that is also given as 3 kilowatt, it is already given to you, you do not have to calculate. The inside temperature is 25 degrees centigrade, outside is 35 degrees centigrade, inside room temperature is 60%, outside WBT is 24, etc., and you have 4 hot plates, each 2 kilowatt are there inside, because it is a restaurant. So, that should be generating heat. So, to simplify this whole affair, we have said it is 2 hot plate, which straight away you can calculate the energy that is coming out of it. Lighting is 15 watt per square meter. For this kind of area, generally National Building Code gives you the area amount of lighting per meter square for different types of occupancies, right. So, the 15 watt per square meter of course would have been based on the earlier days type of lamps. Modern lamps might require much less actually, but whatever it is, here it is given as this. Infiltration is 0.5 air changes per hour. In other words, there is a leakages, all windows will not be sealed properly. So, there will be air gaps, so through which fresh air will come in, and that is we call as infiltration, because that is not by design, that by default, because the construction is not good. So, 0.5 air changes per hour is given. Now, what is air changes? Air changes per hour is the number of volume, number of times room air gets exchanged. For example, fresh air comes from outside, it will displace the room air. Now, if the total volume, total air, volume of the air, which is equivalent to the volume of the room, if it gets changed 3 times in an hour, then we call it 3 air changes. 6 air changes means in 1 hour 6 times whole volume air equivalent to whole volume of the room will be exchanged, fresh air will come. So, you can find out the flow rate 6 into volume of the room or number of air changes into volume of the room, that is the flow rate will be given by number of air changes multiplied by volume of the room in meter cube per hour. You want to convert it into second, then divide by 3600, because flow rate if you want to find out. So, this is given as 3 air 0.5 air changes per hour, the infiltration, and proposed supply air differential is 10 degree. So, as I said that this is pre-decided, differential between room temperature and supply temperature, right. This is pre-decided because we do not want to keep it too high, right. We do not want to keep it too high and again too low. If it is too high, then the insulation required will be, because room temperature is fixed because of from your comfort condition. So, supply air temperature is too high, it would mean that insulation required cost will increase, because you are at much lower temperature, you will be differential is high. So, supply temperature will be lower, you will require more insulation cost. And if supply temperature is high, then you will go to increase the flow rate, because you want to remove the heat, and flow rate increase means size of the piping will increase, and if you lower the size, then velocity will increase, which means that noise might increase. So, therefore, there is a kind of a compromise between all these. So, we keep it at, in this case we have been proposed to keep it at 10 degree. Heat gain from each occupant is 90 watt. right. That is sensible heat gain, means temperature related. And then there is some latent heat gain, because there will be perspiration, even our through our respiration we generally exert some amount of moisture as well along with the carbon dioxide. So, this is 30 watt latent, and heat gain from meal, because the restaurant is 10 watt sensible and 10 watt latent. Now, because the meal are served usually in moist form, so the moisture will evaporate. So, that is what it is, right. The properties of the air is given. Specific heat of air is 1.01 kilojoules per kg. Latent heat is given as on an average basis 2501 kg per kilojoules per kg, and density at 20 degrees centigrade is 1.2 kg per cubic meter. So, we got to look into this problem. So, first thing we calculate out how much is the sensible heat gain, right. Okay, this I think this is a formula related to, I will come back to this GS and all. This is the formula related to how you calculate out. We will come back to this later on, but let us, is it given here? No, the problem solution of the problem is not given. Okay, so let's solve it straight away here itself. We will come back to this, how we calculate the relative humidity. So, if I want to calculate this out, right. So, first thing is I find out how much is the sensible heat gain. How much will be the sensible heat gain? I have first is the average U value of exposed walls are 2 watt meter. So, room size, let me first calculate out. Room size is, to find out the volume of the room, volume of the room is 25, 15 into 25 by 4, right, 15 into 25 by 4. So, that is how much? 1500 meter cube, that is the volume of the room. Okay. Sensible heat gain will have components, that is first thing. Now, this will be required. Now, if it is, because this information I will require. So, I will keep this volume of the room volume is 1500 meter cube. I want to find out the sensible heat gain. It will have a component of heat gain through the walls and all surfaces. So, it is said that heat gain, the average U value of exposed walls are this, and total. So, total heat gain. So, what is the wall area? Wall area 15, wall area is 15 plus 25 into 2 into 4, right. So, this would make it how much? 40 into 2, this would be 8 into 40, 320 meter square. And how much is the heat gain through this? Actually, we are assuming the room below and room above is at same temperature, air condition, there is no heat exchange between. So, only wall I am taking, right. So, it is in some floor in between. So, top level and bottom level are same temperature. So, roof and floor I am not taking any heat exchange. So, area is 320 meter square. What will be the heat flow? The amount of outside temperature is given. Outside temperature is 35 degree, inside is 25, right. So, temperature difference. So, U A delta T. So, U is, it is given 2, right, it is given 2, it is given as 2 watt meter degree centigrade. So, this is 2 into 320 into 10. So, this is part of the sensible heat gain, this is part of the sensible heat gain, right. This is part of the sensible heat gain. So, this will be, so sensible heat gain, if I calculate out component of sensible heat gain, okay. So, this is first is 320 into 20, 320 into that is 64, yeah. 320 into 10, 6000. This is the first one is 6400 watt. This is one. Then let us see what is the other one. Next, this is AI theta. So, is there a glass area given? The amount of the heat flow is given also. Amount of heat flow is 3 kilowatt. Through the glasses, the heat that is coming is 3 kilowatt. You know, the radiation heat gain through glasses is 3 kilowatt. So, I just add that. So, glasses through glasses 3000 watt, 3000 watt, 3 kilowatt is already given. Then from each person, now I must find out how many persons sitting there. 300 persons in 3 sitting in 2 hours. That means in each sitting how many person will be there? 100. And they sit for 2 hours. So, if I want to calculate out how much heat they are generating, that 100 people will generate 90 watt, it is given I suppose, something like that, you know, 90 watt, what is it? 90 watt, each person actually generates heat of 90 watt, right. So, 90 into 100 people, because at any time 100 I am designing for 100 people sitting, right, any time 100 people sitting. So, this will be no for 3 hours, yeah, but it makes any no difference, because I am calculating the rate of heat flow. 2 hours has got no, I keep it open for the restaurant is open, let us say for 2 hours, peak hours is 2 hours, other time it will be less. So, I am designing for the 2 hours period, and where 100 people will be sitting in one sitting, 300 people in 2 hours, in 3 sittings, so 100 people. So, 9000, right, 9000, that is sensible heat. What else is a sensible heat? And from each meal, so I will have 100 meals, let me assume the extreme, the 100 meals, each meal will have 10 watt sensible and 10 watt latent. So, let me take only the sensible heat. So, from meal again I will have 1000. So, anything else heat, anything else, casual heat gain, if there is appliances, lighting how much is 15 watt per square meter. So, I have got how much area, 320, how much area, floor area, 25 into 15. So, that would be 25 into 15 into 15, 15 watt per meter square, no, lighting. So, that would make it 15 into 25, 225, into how much it is, some value, 5625, okay, let us say that. And then I will have some from the heaters, it's there's some heater. What is that heater? 4 hot plates, 2 kilowatts, that means 8 kilowatts, 8000. So, I add another 8000. I can sum this up all and I will get the total sensible heat, but there is one more thing remaining, infiltration. Infiltration is remaining. Now, infiltration heat flow will be 0.5 air changes. So, if I look at this, so therefore, so far if I sum it up, how much does it come? 6400, 3000, 9000, so 12,000, 13,000, 13,000, how much it comes to? 5, 2, we will calculate separately, just I am trying to calculate with some, I don't have to put this down. 6,000, this is 9,400, 18,400, 19,400, 19,400 plus 5,000, 20, 19, 24 plus 25,000, 25, 25,000, 25 plus 8, 25,000, 25 plus 8 is 25, 33,500 so far I have got. I have got 33% 500 so far, 33,500 so far I have got, right. So, sensible heat gain, sum of all this plus this, of course, I have to find it out from infiltration. Okay, 33025, yeah. So that's what it is coming to. So let me write that down. Sensible heat gain. It's all sensible heat gain, yeah. No, all components of sensible heat gain. So far it is 33,025 watts plus the infiltration. Now to find out the infiltration, what is the information given to me? 0.5 air changes per hour. You know, that's the information given to me. Infiltration is 0.5 air changes per hour, which means that 0.5 into volume of the room, which was 1500, right. Lighting we have not calculated. Oh no, we have calculated everything. Yeah, that much would be changed in 1 hour. So that if I want to convert it into watts, number of air changes multiplied by volume of the room divided by 360. So that's the rate of flow multiplied by the density of air, multiplied by density of air into specific heat, multiplied by density of air and specific heat. Now how much will be the density of air? Density of air at this temperature at which it is coming, that is known to us, 1.2, but this air is entering at, you know, how much heat it is bringing, I want to find out. So it is coming at 28 degree, the heat that is bringing is, it would be actually the one that is going out at 21, because room temperature is 21, one that is coming out is at 28. So the density difference, rho Cp difference between these two temperatures I must calculate out, and rho is given by, we know that rho 1 T1 is equals to rho 2 T2. This is for 273 plus 2293 into 1.2 divided by the temperature at which I want to find out the density. So if you are finding out at 28 degrees centigrade, this will be, you know, so and Cp is given, average Cp value is given 101 kilojoules, which means 1010 joules per kg. So that has to be multiplied. So if you multiply that, then you will get the amount of sensible heat gain, right, amount of sensible heat gain. Rho 1 C, you know, Cp 28, it's entering at 28 and going out at 21, the going out. So there is a density difference, specific heat we are keeping as constant, right, and you can find it out how much, you know, the sensible heat gain, because outside air temperature is given as how much, 35, sorry, 25 was the earlier problem, 35 degrees centigrade, and inside is 25. So it is entering at 35, going out at 25. So you can calculate out the difference in densities, you know, multiplied by the specific heat which is given. So you can calculate this out. So let us say it comes out to be another 1000 or something of that order, you know, roughly it is actually 1/3, 1/3 roughly. So this would be n into V. So it will be somewhere around, not much large value, it will be 750 or something. So that is how we can calculate out the total sensible heat gain. That is how we can calculate out total sensible heat gain, right. Now I can calculate out the latent heat gain. Then you do this, you complete this problem yourself, rest of the thing. So then I can do the latent heat gain. How much will be the latent heat gain? Only two sources. One is the number of persons, other is the meal. So from the meal it comes 100 into 10. So latent heat gain will be latent 10 into 100, because 100 persons are sitting at a time. So 1000, and every person 30 watts, right, is given. So 30 into 100, right, that is it only. So it is only 4000 watts. So usually you see sensible heat is much higher than the latent heat gain, you know, latent heat is very small. So what we do? Next step we find out the flow required, mass flow required to remove this sensible heat gain. mass flow required, flow of supply air required to remove the sensible heat gain.